Audience for this is a fundamental general chemistry class, though it can be applied as well to a full-on general chemistry class or general chemistry students as well as organic students. So to start off with, electronegativity. Particularly in a fundamental class, it tends to be a topic that gets kind of ignored and sidelined. It's a really important concept dealing with the ability of an atom to take bonding electrons from another atom. This is going to become important because Lewis structure is all about structure and how atoms interact with each other. So looking at how electrons will shift between individual atoms is electronegativity. So we really need to take advantage of it. As far as what you need to understand, it's just a way or someone measured the ability for an individual atom to take bonding electrons from another atom. Okay, that's it. So it's trying to help us understand where to disperse our electrons in a molecule. General rules: fluorine is the most electronegative element and cesium is the least. Okay, this is opposite the metallic trend if you happen to memorize the metallic trend. Electronegativity is far more important than metallicity. Okay, so I would highly encourage you to memorize this. With that said, we now have a nearpod stop. So here's our first one. Go ahead and advance and take a look at the quiz questions. Remember, might be a good idea to understand why you're answering the questions you've got, because it might be helpful to ask questions about how things were discovered in class. Continuing, how can we then use this to classify our individual bonds? Well, there are three primary bond types, okay, that we're concerned with in most of chemistry. There's another section in there. We have the ionic, we have the polar covalent, and we have the nonpolar covalent bond types. These bond types are primarily classified based on the difference in electronegativity between the atoms in that bond. So if we take a look at that first bond between sodium and chlorine, you might already think or realize that that is an ionic bond. Okay? And well, one of the reasons why it has been classified as an ionic bond is that the difference in electronegativity between sodium and chlorine is greater than 1.7. So we would look up the electronegativity for sodium, shown as a chi symbol, and we would subtract the electronegativity for chlorine, and we would look at that number. That value happens to be greater than 1.7, which then means we have an ionic bond. We can use this same logic for the other bond types. You'll notice the nonpolar covalent, I've got the note that it's less than 0.5, so a very, very small difference in electronegativity. Polar covalent, I didn't classify it because it's the one sitting in between. This definition is all fine and dandy, except it then requires that we have our electronegativities either memorized or constantly available. Okay? And both those situations are fairly rare. Okay? So we want some kind of rule of thumb to help us approach this. Well, that rule of thumb, depending on your level, you may already have started to memorize. Your ionic bond classification is very typically a metal bound to a nonmetal. So that stands out, very easy to nail down. And if we look at our trends in electronegativity, your metals tend to be very low in electronegativity, and our nonmetals tend to be very high, which then means when we look at the difference, we get a very large difference that matches the exact definition, okay, of that 1.7. We then run into an issue when we move into the polar covalent and nonpolar covalent. The issue is this: both of those are nonmetal to nonmetal bonds. How do we then classify or differentiate between the two of them? Okay, so we can add that information here. So how do we subdivide those? Okay, well, that's going to come down to, again, our kind of difference in electronegativities. Okay, the nonpolar covalent bond is one that has a very, very tiny difference in electronegativity. Okay, so when would we have a very small difference in electronegativity? Well, one example is already kind of given for you. What if we have the same element to the same element? If we have that situation, the difference in electronegativity is actually going to be 0, which by definition is less than 0.5. So this works. Okay? The issue with that is a little bit too narrow of a definition, so we want to broaden it ever so slightly for a bond that we might commonly see and use in the real world. Well, that bond happens to be carbon to hydrogen. Okay? So we now know an ionic bond is a metal to a nonmetal. A nonpolar covalent bond is the same element to the same element, or carbon bound to hydrogen. So we've got some kind of simple classifications for those two. Well, then what happens with our polar covalent, which is left over? Okay, well, that one's a bit annoying because it's that weird difference in between. So what I like to do is memorize the difference or definitions for our ionic and our nonpolar covalent, and the polar covalent I'll just say is everything else. Okay, so I will apply my definition and say, okay, where does it fit? Does it fit in box 1? No. Well, does it fit in box 3? No. Well, then it fits in box 2. It's a polar covalent. Okay. These classifications are super, super important, kind of on a smaller extent for Lewis structure, but super important to understanding of chemistry in general. So we'll keep coming back to them, which is why you need to be looking at defining these. When we're looking at our Lewis structure, we're primarily concerned about our polar covalent and our nonpolar covalent bond systems. Okay, so when we're looking at Lewis structures, that's our primary focus. We'll ignore the ionic or the metal-metal bonds. Okay? So, when we look at our periodic table, we've got our electronegativity trends that we need to be able to manipulate, and we now want to go through and try and predict something about bond characteristics based off of this. So again, I'm going to have you stop here, work through some classifications on bond types, and then we'll go ahead and continue on. The real gist of it, which is our Lewis structures. So Lewis considered atomic structure. Okay, so we have electrons, protons, and neutrons, and we've got some basic understanding of orbitals at this stage, or when Lewis entered the scene. And he wanted to come through and explain why certain atoms combine in different ratios. So if we take a look at the examples listed across the top there, if we take hydrogen and we bond it to hydrogen, well, we only form one bond. Okay? We bond that to fluorine, we only get one bond. We bond it to carbon, I now need 4 hydrogens for 1 carbon. Well, why does that ratio change? If we go through and look at the nitrogen and the oxygen, same situation. So it starts to change. So something about how those atoms are interacting with each other changes their interactions. Okay, so what he went through and did is try to simplify this down. You'll notice that all of my examples are in the first 2 rows of the periodic table. And that's because we have the simplest orbital arguments in those situations, so it makes life a little bit easier. When he went through to evaluate this, he looked at the maximal number of electrons. And if we look at that second row, our maximum number of electrons is 8 electrons. So, okay, well, 8 electrons, I'm probably looking at a cube, because a cube has 8 points. So what he went through to do to evaluate each and every single one of his potential structures is he took the electrons from each of the atoms. So notice we have the electron configuration for hydrogen on the left, and we have the electron configuration for fluorine on the right. You might say, well, aren't I missing the 1s2 electrons? Yes, but this is where Lewis's theory kind of takes a leap. Okay? He decided to ignore the 1s orbital in the case of fluorine. And that's because there were electrons further away that would more than likely interact with another atom. So we only look at the valence electrons in our configuration when we're looking at Lewis structures. Okay? So then he said, okay, well, if I've got these 2 cubes, I'm going to go through and fill it out. Well, I've got 1 electron in the case of the hydrogen, and for fluorine, I've got a whole lot more, which I don't really want to draw all out. We've got all those points. And if we look at those connections, we'll notice that if I bring these 2 lines or sides together, that red electron can fill the vacancy in the fluorine, and that purple electron can fill the vacancy in the hydrogen. Okay? So he's looking at ways to get these 2 structures to interact with each other in such a way that they satisfy and fully fill their octets. They're octets getting to the noble gases, which don't interact with anything because their octets are fully filled. So he's trying to come up with a model that allows for this. If we then try and scale this up to larger and larger molecules, theoretically we can, but you'll notice trying to draw cubes for everything is a bit tedious. So what we end up doing is simplifying it. Let's go ahead and we'll stick with the HF example for the moment. Is that we'll look at hydrogen and we'll look at fluorine, and as we bring those two to each other, we can end up saying that on one of those sides we have, or each of those sides, we have a pair of electrons. And this is only slightly different from that previous drawing. What we now have is, instead of a three-dimensional cube, we have a two-dimensional square. So focus, at least in fundamental chemistry, and for that matter organic chemistry, on placing electrons on the face of a square for each of your atoms. That will allow you to see the bond connectivity between the atoms and allow you to understand Lewis structures a little bit easier. Okay? So, here are my rules for going through and assigning Lewis structures. I would highly encourage you to pause and read through these and make sure you follow them. Okay, for the most part, they're the same as every other rule set that you'll find out there, but there are some subtle differences. Okay, that big difference, number one, is right here with step 3. Okay, we want to add electrons in pairs to the most electronegative atom first. This is why electronegativity becomes important. Okay, and I like to refer to this as the noble rule because we're satisfying the octet. We'll add them until we've achieved 8 electrons around our atom. Okay? We'll continue to add electrons until we've added all the electrons that we could possibly add according to step 1, totaling our valence. Okay? This subtle difference will help you identify resonance later on. Okay? If you decide to use any rule set I've seen out there other than this, you will have a much more difficult time identifying resonance. Okay? For those of you that are trying to get into organic chemistry, resonance is the answer to everything you want or need to know. Try and set up and do your Lewis structures in this fashion, and it will help you achieve and understand resonance quicker and easier than the other methods that float out there. Okay? So again, take a second, pause, read through it, make sure you understand it, and now we'll advance. With my simplified version, let's take a look at a couple examples. Okay, we'll start with H2O. So, I want to total the valence electrons. So in step 1, I've got hydrogen with 1 valence electron. I've got oxygen with 6 valence electrons. Okay, so well, how did I pull that out so fast? Let's take a quick look at our periodic table. Hydrogen, this was a horrible table to use. Hydrogen is located in column number 1. Interesting coincidence. Oxygen is located in column number Roman numeral 5-1, happens to be 6. Your valence electrons are given to you in the Roman numerals above each of your columns, at least for the ones that you'll be using. Okay? So take that into consideration. It can help you get through these quicker and easier. So if we go back, we said our hydrogen had 1 electron, oxygen had 6. There are 2 hydrogens, however, so I will multiply that by 2, and I will end up with a total of 8 electrons. Okay, that is step 1. Step 2, I need to pick a central atom that is the least electronegative. Well, hydrogen is lower in electronegativity than oxygen. However, if you go back to the full rule set on that previous slide, we need to make sure we pick the atom that can bridge. We have to have multiple bonds. Hydrogen can only have 2 electrons around it, which means it can only have 1 bond. That means in this case, we kind of have an exception to rule 2. So I will place my central atom. We'll then place the other atoms around it. Okay. Notice that I'm placing them symmetrically. It doesn't really matter though I am trying to focus on placing them on the faces of a square for that central atom. I will now add electrons into my structure to the most electronegative, which in this case is the oxygen, and I will add them in pairs around that oxygen. Okay, I will continue to add electrons until I've achieved my total. Well, I've added my 8 electrons, so I cannot add any more to the structure. I'm done with that. So I now move to step 5. In step 5, if I have a pair of electrons between atoms, I turn it into a single line. If I have multiple pairs between atoms, that just means multiple lines. There we go. Now we have to check our octets. Okay, well, if we look at our hydrogen, that becomes a bit challenging, because if we look at the hydrogen, it only has 2 electrons associated with it. That line are electrons being shared between the hydrogen and the oxygen, so hydrogen has both of those. Well, 2 is not 8. What's going on here? Hydrogen does not need to go to the octet rule, or follow an octet, because it can't have that many electrons being only in the first row. Its octet is indeed satisfied at 2. If we go through and take a look at the other hydrogen, same situation. Our octet for that hydrogen is 2. The octet for our oxygen, because it is not hydrogen, is 8. And if we go through and evaluate, everything's now achieved its octet. So I do not need to worry about anything else in Rule 6. All of my octets are satisfied. There's nothing to move around. You'll notice that I have resonance under step 6. So since step 6 is done, resonance we don't need to worry about. In step 7, I've crossed formal charge out. So at this point, you don't need to worry about formal charge. So what we now have is the full Lewis structure for H2O. Fantastic. Simple, straightforward. Okay. Go ahead and pause the video for a minute and go through and solve for CBr4, or carbon tetrabromide, and I will show you the answer here in just a matter of seconds. So we've got the answer magically appearing, or most of it here. We've got our total valence electrons. We've got carbon as our center atom because it's the least electronegative. I started adding electrons to the bromine, though that's not obvious, but we can show that with the last one. I'll put them on the bromine first, and then in between the carbon and the bromine, okay, because bromine's more electronegative. We've now achieved all of our electron count, assuming I did all my counting right. We can convert pairs of electrons into lines so long as they are between atoms. Rule 6, octets are all satisfied, no resonance, no formal charge. I now have the final structure. Okay. I do want to add step 5. There are some teachers who, for lack of a better descriptor, seem to either be of the older generation of chemists or were trained under the older generation and then don't want to change, that will show pairs of electrons regardless of whether they are bonding or non-bonding as a line, as I've shown with the rightmost bromine. I personally find that very confusing, because then what does the line represent? Well, it only represents a pair of electrons. There is now no difference between bonding and non-bonding pairs of electrons unless they're shown between atoms. I think that can get confusing. I will always show my lone pairs, or non-bonding pairs of electrons. I will never show them as a line. It's a personal preference. Nobody should take off points for that. Okay. So at this point, we've got our periodic table again, so you can go through and take a look at that. We have another near-pod stop. Go in and do some practice, answer some questions about some valence electrons, and drawing out some Lewis structures. After you're done with that, we will continue into Lewis structures. Again, another example. This one's a little bit more challenging. So if you'd like to pause the video now, not a bad idea, and try to solve for the Lewis structure on your own. For those of you that wouldn't want to go all the way through it, you can now start to watch. Sulfur and oxygen both carry 6 electrons. There are 3 oxygens to account for. So I'm looking at 24 electrons needing to go into this structure. Okay? Between sulfur and oxygen, sulfur is the least electronegative, so sulfur is going to be my central atom. I'm going to try and draw it with plenty of space. I'll then put my oxygens around it. I'll then start to place my valence electrons. So 2, 4, 6, 8. Okay. Here's another 8. And another 8. And I now have all 24 electrons. Okay. Again, notice that I'm placing it on the square of my center atom. I'll convert pairs of electrons between atoms into a line. And I've now finished step 5. Before we say we're done, we have to look at satisfying the octets. The oxygens, you should hopefully see by now, all have 8 electrons. The sulfur, however, is at 6 electrons. Okay, well, octet means 8, so as long as we're not in that first row, which sulfur is not, that octet had better be 8. So I've got a problem here. I need to fix my structure because it does not accurately represent the balance of electrons. Sulfur is missing electrons. To do that, that's where step 6 comes in. We will satisfy the octet by moving pairs of electrons from a different atom towards the sulfur. I'm being very careful in my word choice here. If I take, say, this pair of electrons that I've circled in blue there, and I give those to the sulfur, what happens? Well, the sulfur picks up a pair of electrons. The oxygen's missing that pair. Well, now my sulfur has how many electrons? Well, it should have 8. All's good and well. So we'd say happy, and now we're done. But now you have to evaluate, because you've moved a pair of electrons, that oxygen. How many electrons are around that oxygen? Now it's 6. Screwed up. Our structure is still missing electrons. Okay. Well, here's the next big common mistake that happens. I'm just going to give it 2 more electrons. Well, now it has its octet. However, how many electrons are now in the structure? We now have 26. Okay. One of our big cardinal rules is we totaled the valence electrons for a reason. We can only put 24 electrons into this structure. I don't have 24 right now. I have 26. I cannot add more electrons. So something has to happen with that pair of electrons. Okay, that was on the oxygen, now is on the oxygen. I can't just straight up give it to the sulfur because then the oxygen misses them. I need to place those electrons in a location where both the sulfur and the oxygen have access. Where is that? It's between the sulfur and the oxygen. So if I redraw that, what I would then end up having is another pair of electrons between the sulfur and the oxygen. Revert to step 5. Pairs of electrons between atoms can be turned into a line. There we go. Simple as that. We've now got our fantastic Lewis structure for SO3, and we might be happy and move on. However, why did I take the electrons from that oxygen? Were there no other choices? Was that the only oxygen possible? It turns out the other 2 oxygens were equally valid sources of electrons, which means I could have just as easily drawn the structure like this. Kind of forgive the pause here. Or I could have drawn it like this. Okay, well, now we run into a dilemma. Which of these structures is the correct structure? That's all we focus on in chemistry, right? Is the right answer. Okay, well, this is where resonance comes into play. Okay? There is no difference between these 3 structures. Okay? That means, with being all the same energy and the arrangement of the electrons being different, we have to draw all three. We have three valid resonance structures that need to be included. So being asked to draw the Lewis structure, or structures, for SO3 is a bit mean because you have to draw three of them. Three are required for the fully correct answer. Okay? And this is where resonance becomes challenging because you often want to forget about drawing those other structures. This is also why adding the electrons to the most electronegative comes in really handy. Okay? Remember, we started here, okay, with our central structure, with the sulfur missing a pair of electrons. Because we placed the electrons on the most electronegative, we now see a vacancy on that sulfur, and we need to satisfy that vacancy by moving electrons. If there is more than one source of electrons, I must use all possible sources. Okay? And I end up with three possible answers, the double bond being between any one of those three oxygens. Okay? Yes, it is a challenging concept, but you should be able to work through it. Unfortunately, I don't have practice for this one, at least not in the video, so if you got questions about it, ask in class. We'll probably work through a couple others in class as well. This is kind of the end of the fundamental understanding of Lewis structure. Okay? So there's some pretty big concepts that were not covered here. Formal charge, which I'm giving you a formula there, which is slightly different than what you'll see in textbooks. And ranking the quality of your Lewis structures. Okay, these are two massively huge concepts. Depending on your level of chemistry, you may or may not need them. Formal charge is typically brought up in first semester general chemistry instead of fundamental. And the ranking of quality of Lewis structures really kind of oscillates between first semester general chemistry and, for sure, organic chemistry. To really rank the quality, you must understand formal charge. Okay? If you're in the fundamental class, please go ahead and stop the Nearpod, or stop the video, advance into the Nearpod, just asking some kind of wishy-washy, how do you feel about this video kind of questions, okay, at this stage. If you need to know about formal charge or ranking of quality, then please continue on with me. So charge is a nebulous concept that takes some careful explanation and very careful differences in your terms. Really what it's looking at is the balance of electrons. Okay? So we use charge earlier on in our Lewis structures by either adding or subtracting electrons for our total valence electrons. So if we had a negatively charged molecule, we had to add electrons. Okay? In Lewis structures, what they're showing is how the electrons are distributed through the molecule. And it pretty much ignores this concept of charge. It's just saying the electrons are there. Okay? Formal charge is kind of an addendum to Lewis structure. It then specifically looks at each of the individual atoms and says how are the electrons in the molecule shared around that atom. Okay? Its big assumption is that all of the bonds in that molecule are perfectly covalent. They're being equally shared, or equal sharing of electrons. Then we end up with the formula shown. Formal charge equals valence electrons minus non-bonding electrons minus the number of bonds. There is another way we could have looked at this. We could look at this according to an ionic bond. And in that case, we would call it oxidation state, okay, or oxidation number. It's how the electrons are distributed in atoms, just like formal charge, but now we're assuming a perfectly ionic bond within that situation. Calculation's a little bit easier. It's your number of valence electrons minus the owned electrons. Okay, owned gets a little bit nebulous. If you need it, talk to somebody, ask them about it. I'm not going to talk about it for the sake of this video because it's not particularly relevant or used for Lewis structure. We typically use formal charge. Okay? So that's the one to focus in on. That's the one that you need to memorize that formula, if you will, for how to calculate it, because it is going to be super important. So if we go back and look at SO3, okay, we want to come up with some idea for how these were all valid answers. Okay, well, we can use it with our Lewis structures to eliminate bad structures. We'll maybe by going through and looking at these, we can say, well, one of them was bad, we didn't have to show it. It turns out that's not the case, but we can go through and evaluate it. Because it is an atomic assignment, I would go through and look at every single atom. Oxygen comes in with 6 valence electrons. The number of non-bonding electrons, not pairs, non-bonding electrons. There are 1, 2, 3, 4, 5, 6 non-bonding electrons. Minus the number of bonds, it has 1 bond, and I end up with a total of -1. That means the formal charge on that oxygen is a -1. To add that information, I could write -1 next to the oxygen. I would then go through and do this for every atom in the structure. Okay? If we do it to the rightmost oxygen, you should notice that you'd see a -1 as well. The other way to abbreviate it, particularly if it's only a 1 value, is you'll typically see me circle them, okay, as negative or positive. We look at the topmost oxygen, okay, and do its calculation. We did it with 6 minus 4 minus 2, which gets us 0. So we could write 0 next to it for its formal charge. That's a bit redundant, so what we'll do is anything that is 0 charged we'll ignore. The last one are sulfur in the middle. Sulfur comes in with 6 minus the non-bonding electron. Well, it doesn't have any, so that's 0. Minus the number of bonds. Well, there's 4 bonds. This gets me a charge of +2. And I would need to specify that charge next to the sulfur. I've now assigned formal charge to every single atom within that structure, and I've done the work I need to, or the due diligence for that. Okay? As a good way to check our work, if we look at the charge specified in the formula, upper right-hand corner, there is no charge written, which then means the formal charge for this molecule must be 0. But I have a -1 and a 2, what's going on? It's the overall charge. -1 plus 2 minus 1 gets us 0. So we have 0 formal charge in that structure. Okay. Depending on how good you are at recognizing patterns, you should be able to see, if not see immediately, go through and do the calculations, and verify that the other 2 structures are going to end up with the exact same formal charge alignment. Okay? So with all of them being of equal charge, there's no way to distinguish them. They're all the same. You have to provide all 3 structures. Okay? Where this becomes more useful is looking at, say, structures that have bad resonance or bad formal charges. So if we take a look at the formula for CO2, okay, and if you go through and do all your rules, which you should be able to do, you should end up following my rule set up to step 6 at this point. Okay, and we should notice that the carbon is missing its octet, and we need to satisfy it somehow. Okay, so we could move a pair of electrons in. So I'm going to move a pair of electrons from the right side in, forming a double bond. Okay, if we now go through and check the octet again on the carbon, it's still missing its octet. Okay, here's the dilemma. I still need 2 more electrons. Where do I get those 2 more electrons from? Depending on how you are taught to draw Lewis structures, you may very well go through and say, well, I will take them from that left oxygen and I will end up with that structure. And that structure is not wrong. In fact, it is correct. And if you look up the Lewis structure for CO2, you will find that. However, why did you draw that? Was it not equally valid to go through and have taken a second pair of electrons from that last oxygen? Does that not equally satisfy the octet rule for all 3 atoms? And who's to say at the very beginning that I should have taken them from the rightmost oxygen? What if I had taken them instead from the leftmost oxygen? Okay, well now I have a problem. I have three structures, and I have no way of distinguishing them up to formal charge. When we bring formal charge into it, what happens? Go through and do your calculations. You will find that for your center structure, the formal charge on both oxygens will be 0, and the carbon will be 0. If you go through and calculate the formal charge on the rightmost structure, you will find the leftmost oxygen is -1, the carbon is 0, and the rightmost oxygen is +1. If we check it with our purple structure, we end up with the inverse. All of these total to satisfy the formal charge given for CO2, 0. But the two structures on the right and left have also included charge, or a formal charge. Why are those structures ignored? Okay. Those are ignored because we're now differentiating good versus bad. And one of our rules for deciding Lewis structures is to minimize charge. So I want the smallest amount of charge possible. If I look at the center structure, there is no charge whatsoever anywhere in the molecule. The left structure has 2 atoms that are charged. Well, which is better? No charge is better. Okay? So that means the center structure is better than the left structure. So I'll cross out the left structure. I shouldn't draw that because it's not a good one. What about the rightmost one? Well, the rightmost one runs into the same issue. It's charged. So it is not as good as the center structure. So I would eliminate that one. By using formal charge, I can then narrow down that when I look for CO2, I'm only expecting one structure. I don't expect to see the other two. Okay? And I don't expect to see the other two because of formal charge. If you do not know how to do formal charge, both of those other structures are equally valid. And that is a challenging concept to get through. Okay? So, when comparing several Lewis structures, you need to draw the best. The best must follow certain rules because this is an arbitrary human system. We're just establishing what those rules are. Rule number 1, you must complete octets. Okay? Even if that means putting a charge on an atom that you don't think should have that charge, you need to satisfy the octet. That is your first and foremost rule. Complete the octet. After you've completed the octet, then you need to minimize charge. So, number 1 option, less formal charge across the molecule, okay? Or make sure the charge is appropriately placed. For instance, if I had a molecule where I could put a negative charge on oxygen or nitrogen, where should I put the negative charge? Hopefully you would say on the oxygen, and that's because oxygen is more electronegative than the nitrogen. Okay? If all is equal at this point, then you really do have resonance officially, and you should draw all the possible structures. There are some other subsets of rules that follow out of this. Those tend to show up very infrequently. You're really only looking at those first 2. Okay? This does require practice more than any of the other parts because you actually now have to interpret the structures drawn, not just draw them. Okay? So, with that, we'll move into our next topic of shapes of molecules. So Lewis structures do a great job of representing how many and what type of bond, but it does a horrible job of describing where they are in 3-dimensional space. If we look at the Lewis structure for methane, or CH4, oh, that's kind of irritating, we should end up with that structure in the upper left. Okay? What that doesn't help us understand is that the bond angle actually found in methane, okay, is not accurately shown in the Lewis structure. That bond angle looks like 90 degrees. But when we look at methane, methane has all hydrogens equally the same. There's nothing different about any one or the other. And you might go through and say with this Lewis structure that that is the case. All of those are 90 degrees. And all of those marked are 90 degrees. But what about that one? That bond angle is 180 degrees, which means we have different hydrogens. Okay? You look at the actual molecule, it does not have different hydrogens. They are all equivalent. That means Lewis structures fail at describing the shape. This does not mean we ignore them, because Lewis structures are phenomenally good at describing the bond type and how many bonds and how individual pieces connect. It just doesn't explain where they are in three-dimensional space. Okay? A good way to think about it is we took a three-dimensional object and we turned it into a square for our center atom, which was a two-dimensional space, to simplify it. We didn't want to draw things in 3 dimensions because it would suck to draw them in 3 dimensions. Okay? So what we need to be aware of is that we're actually looking at these molecules in 3 dimensions, and there are better ways to represent them. So we've got that nice little rotating GIF in the middle to explain what's going on, or show that they aren't all 90 degrees. Okay? And if you look to the far right, you'll notice that we can also accent the difference in those bonds, or their spatial awareness. This wedge means it's coming at you. Okay? And the dash means it is going away. So it's behind you. If we look at how the video actually froze, we have the in the plane bonds, plane of our paper, and then we have the coming at you bond, and we have the going away from you bond. Okay? We're just trying to represent that a little bit better. This is where model kits come in handy for those of you in organic chemistry. For those of you that just want to get through your Gen Chem class, don't stress on the model kits, at least not yet. Can be helpful, but not a big deal. We want to get into a new theory now, which is valence shell electron pair repulsion, okay, also known as Vesper. It makes an assumption that the electron pairs will repel away from each other to get as much three-dimensional space as possible, which makes sense. You're taking similar charges and bringing them near each other, much like the north end of a magnet and the north end of a magnet. You bring them close, they repel. You bring the north to the south, they attract. Okay? When looking at our Vesper model, we will look at 2 potential geometry changes. One is an electron geometry, and this is based on our electron groups, and we'll have to define what those are in a little bit. And then we've got our molecular geometry, and this is shape based on bonding versus non-bonding electron groups. Okay? So let's take a look at the 2 structures shown below. So let's draw a box around our center atom for our methane. So we want to be concerned about the shape typically on our center atom. And we want to say how many electron groups are there. This is where that box comes in handy. That box has 4 faces. Are there electrons on this face? Yep. Okay. Are there electrons on this face? Yep. Okay. For those of you saying, why am I saying yep? What does that line represent? Those lines represent electrons. Okay, so there we go. There are electrons on the next face. Yep. Electrons on the next face. Yep. There are 4 groups of electrons on our carbon. That's it. That's all I want you to be able to do. Sort of. Okay. What about the next molecule? So again, let's draw our center atom. Okay, I'm going to define it on the carbon, and we'll see in a second that I can define it wherever I want, but the carbon again, center atom, typically the one we're looking at. Are there electrons on this face? Well, no. Okay, there are no electrons there. Are there electrons on this face? Yep. How about this face? Yep. How about this face? Also. So how many electron groups are around that carbon? Okay, well, 3 faces had electron. There are 3 groups of electrons. Okay, and you might actually be wishing that you could scream out and asked me a question. So I'm going to predict that that question that you are asking about is on that face. Aren't there two groups of electrons there? No. There are two pairs of electrons there. There's only one group. Those electrons are being occupied in the same space between the same atoms. That is only one group of electrons. So I do not count that as two separate groups. It's only one. Okay? So let's switch this up again, because we have another example that we can work here. Now I want to know what is happening with the oxygen. How many electron groups are around that oxygen? So the same idea. No. Are there electrons there? Well, what do two dots mean? Two dots mean electrons. So yes, they aren't bonding, but I don't care about bonding or non-bonding at this point. I just care, are there electrons? Next face? Yep. Last face? Yep. There are three groups of electrons on the oxygen. Okay? So hopefully that helps you explain what's going on with those groups. We now need to interpret those groups into a name. And for those of you saying, why on earth would you ever have to do that? How many math classes have you taken and enjoyed and been like, oh yeah, I totally love going to math? Okay? You will probably find the majority of people don't like going to math, which is arguably a bad thing. Okay? But what we do as scientists is convert the math into something else. We convert it into words. And that's where we encounter these names associated with them. Okay? So we looked at a three-group structure, and we looked at a four-group structure. So methane at CH4 comes out at an electron geometry at tetrahedral. So if I count four groups of electrons, it's called tetrahedral. In the other case that was formaldehyde, that was our CH2O, that had three groups, that is known as trigonal planar. Okay? So you have to associate the names with those number of electron groups. Okay? And we've got some shapes here that I found kind of useful in the textbook that shows some kind of spatial relationships between those individual groups. Okay? Depending on where you go, if you're going to Chandler Gilbert, we've got an awesome tutoring center that has a phenomenal summary of electron groups, much like I've got shown here. This allows us to decide what our electron geometry will be. So are there electrons present on a given face? Okay? That face is either a square, in the case of fundamental chemistry, okay, or organic, most commonly. Or if you're in general chemistry, sorry, you have to look at a cube that's looking at your 5 and 6 electron groups. Okay? So at this point, go ahead and hit a near-pod stop, go out and do some practice, see what you can come up with. The next part of this is, are all electron groups the same? Okay, so if we take a look at ammonia with a formula of NH3, we should hopefully come up with a Lewis structure that looks something similar to this. Okay? And if we go through and look at our electron geometry, we would say 4 groups of electrons, which we would then also say as tetrahedral, which was the same classification as methane, CH4. Well, if all's fine and dandy, that would suggest that the angle between these two hydrogens should be the same as the angle between the hydrogens in methane. So what we did is went through and observed that angle in methane and saw that it came out to be 109.5 degrees. Okay? So ammonia, we go through, we assume it's 109.5, we go through and test it, and it comes out at, I believe, 107.5. And not a lot different, but different. Okay? Why did it change? What's the difference between methane and ammonia? Yes, nitrogen versus carbon, but as far as size goes, they're about the same. So why all of a sudden a different bond angle? Well, it comes down to the nitrogen has a non-bonding pair of electrons. That non-bonding pair of electrons is different than the bonding pair of electrons in methane. That forces a change in shape. Okay? When it comes to lecture, I'm going to ask you to explain that change in shape, so see what you can come up with. Okay? But ultimately, it changes the shape. So we now have to go through or changes the bond angle, which then means we have to come up with a new definition for the naming of our structure. And we'll end up calling it molecular geometry, because in molecular geometry we will not treat all electron pairs the same. We will treat them as bonding and non-bonding. When we subdivide out, what we end up finding out is that we end up with a whole bunch of extra, sorry, I thought there was some extra things in here, but that NH3 comes in as a subclassification. Okay? A lot of stuff on here, so let me kind of clean some of this up a little bit. When we look at our NH3, we're in that tetrahedral electron geometry, or as this slide is showing, spatial geometry. Okay? But we then also have a non-bonding pair of electrons. That non-bonding pair, because it's occupying space, prevents the structure from being trigonal planar, but it also prevents it from being purely tetrahedral. The bond angle changes. Okay? What name do we associate now with this new structure? Trigonal pyramidal. Okay? Why? Because we felt like it. Okay? I wish I had a better example or explanation than that, but that's really all it is. Okay? If we look at some kind of representative structures, methane, CH4, nice and symmetrical is our tetrahedral example. Ammonia is our trigonal pyramidal. Water, drawn kind of oddly there, is our bent example. And the last one, borane, just because, is a trigonal planar example. Those are probably the four most common arrangements that you will encounter. Okay? And I'm probably only saying that because I'm an organic chemist, and that's really what we deal with in organic chemistry. Okay? If you happen to move into general chemistry, so first semester general chemistry, you will have to then be able to interpret the shapes underneath, okay, underneath that red line. If you are in fundamental or organic chemistry, zippity-doo-dah-day, you only need to worry about that top portion. Okay? So that makes things significantly easier. And again, the difference comes in on deciding, is it bonding or non-bonding? How many of each do we have? Okay. To help with that, we've now got everything summarized on here. You'll notice that I've only gone up to 4 groups for our electron geometry, because that's all I really care about. If you need the 5 or 6 groups for your electron geometries to get those molecular shapes, check your textbook or go back and add slides, or take the information from this slide and add it into an Excel file for this one. Okay. With that said, we now have the end of our shape summary, I believe the end of lecture. And the end of our lecture slide. So please go back to Nearpod, answer some brief questions, and let me know what you think about the video. I appreciate your help.